Good morning. It's really nice to see everyone here. I'm really excited to present. My name is Tej, and I'm going to be presenting my work on low shot learning and pattern separation using cellular automata integrated CNNs. This is a small part of my thesis, which I'm hoping to propose and defend in the future. I work in the neuromorphic AI lab under Dr. Dhireesha Kudithipudi at the University of Texas, San Antonio. Thank you, Dr. Emon, for introducing me as well. Okay, so let's get right into it. So I'm going to break up my talk into a certain number of sections, the 3 sections. And the first section is we're going to talk about what cellular automata are and the system architecture that I'm developing to kind of bring this to light. So we're going to talk about what cellular, a small introduction to cellular automata, and also the different types of kernels that we are developing to help evolve these structures. The second section is going to be a static pattern separation. So we're going to be talking about exactly what that is, the data set that was generated to be used with it, as well as how we're training the cellular automata to perform that. And also the role of entropy, which is our magic ingredient. And the third section will be temporal pattern separation, where we extend the static image separation into a series of temporal structures. This will extend the reach of the CA. So section 1, which is the cellular automata system itself. So a quick introduction to what cellular automata are. Well, essentially, they can be defined as a mathematical model that governs a set of operations of a set of similar and identical entities to help dictate the replication, the behavior, the instruction within a mutually cohabitated environment. So that's the technical definition. Simply put, it is a grid matrix of cells that interact with their neighbors and then determine the future step of the future state of the cell, and periodically evolve to perform either operations or just exist. This was initially theorized by John von Neumann himself back in 1950s, 1960s. And he actually worked this out on paper before he had a computer with him. So it was quite remarkable. But then it was later popularized by John Conway, who turned it into something that we call the game of life. And a simple way of seeing how he developed the rules, as you can see on the right, those are the kernels that operate on this grid and dictate how the cells evolve. So simply put, a simple kernel that was proposed by John Conway was if there are 2 or 3 neighbors alive around a cell, the cell stays alive. If there are any dead cell, that means any inactive cell with 3 live neighbors becomes active, and any other configuration of the neighbors will result in the cell staying as it is, or the cell dying. So these were the initial set of rules that were created and that's running this simulation. But over time, people experimented with a lot of different rules, and that led to a lot of different types of evolution. So what we're going to do is we're going to explore different ways of looking into these rules and evolving these rules to attain our goals, what we wanted to do. So a quick look at the different type of cellular automata. So there was John Conway's 2-dimensional matrix cellular automata where everyone has 8 neighbors. There's John von Neumann's, which has a hidden state, and that dictates the next state. So it's not only related to its neighbors, it always has a directional state. There can be more dimensions introduced where every cell doesn't have just 1 or 8 neighbors. It could be a hexagonal system, as we see here, where they have more than 8 neighbors. And also it allows for more communication. And then we can have multi-dimensional cellular automata, which operate in more than 2 dimensions. But for the use of this, But in our work, we've only been using the two-dimensional cellular automata, and I'll explain why. As you saw, the previous kernels that we used, that is the operating function that decides the next state of every cell, we looked into expanding the operating kernels and also expanding the number of kernels that operate on every cell. So here are 4 kernels that I proposed to really help augment the productivity of the cellular automata. So the first thing is the domain, which is the actual distance from the cell itself, and how the distance from the cell, its neighbors, how that distance affects the cell. The second one is the cell activity. This basically tracks how active a cell was over a period of time and how it will affect its neighbors. And you can have a multi-valued cell level keeping track. It's like a history. There's also the cell hierarchy, where you can specify, where every cell will have a hierarchical position, where some cells might be more important than other cells. So that also factors into how they evolve. And there's also cell relations, by which you can dictate whether one or more cell next to it affects that cell positively or negatively. So yeah, so your red could be positive and blue could be negative. So how I'm proposing we put all this together is, so you have your normal cellular automata, and you would have all these kernels operating on different attributes of the cellular automata system. Normally, you only see the upper board, which is the final state of a cell, which is active or inactive. But every state, we can break that up into multiple attributes. So you can see here, every cell shown over here, we can model this as a combination of multiple attributes. Here, the attributes are the domain, the activity, the relation, and the hierarchy. And we can have them as a weighted sum of this passing through a function, and then having a comparator to decide whether it's an active cell or an inactive cell. And then the operation is the same. It basically is a kernel that passes over every cell in the matrix and then decides the next state of that cell. But just to note here that while the cell attributes will all be unique, the weights by which the cell attributes are multiplied are shared between all the cells in a grid. This is just to reduce the number of optimization parameters and keep things uniform throughout the grid. Okay. So why am I talking about cellular automata? So I was looking, at recent research, and there was recent research in where they were using cellular automata to classify MNIST digits. They were using cellular automata for repairing images. And what became apparent to me was the ability of the cellular automata to exploit spatio-temporal dynamics. So it's really good at, identifying correlation between it and its neighbors, which is very similar to what every pixel does in an image. It talks to its neighbors, and it has information which is shared between every neighbor. And I thought that, hey, maybe we could exploit that. So where else do we see exploitation of pixel data in two-dimensional images is in convolutional neural networks, where convolutional operators pass a filter very similar to a cellular automata system. The convolutional filter is passed over the image and it extracts particular features. So I was like, okay, these processes are quite similar. What if we could use the cellular automata to replace convolutional layers in a convolutional neural network? So the reason why I'm exploring this is to help reduce the number of convolutional layers and also see if we can completely eliminate them. And that's a secret, so we'll come to that at the end of it. So let's go into exactly how we're implementing this. So I propose this architecture where we have our cellular automata system with the kernels, and we basically remove a set of convolutional layers from a deep convolutional neural network, and basically pass the input to the cellular automata and your input image onto the cellular automata, and then process it and then pass that to the neural network, a stage in the neural network. We need to first train the cellular automata system. And for this, instead of training on the target data set, I wanted to see whether we could train the cellular automata without exposing it to the target data set at all. So while training, we actually train the cellular automata for universal, I don't want to say universal, so I'm going to say generalized pattern separation. So we created our own data set using Perlin or harmonic noise instead of white noise, because white noise is extremely disharmonious, which does not really translate to any real world scenarios. So instead we use Perlin or harmonic noise, which is present in most natural images. So we use Perlin and harmonic noise, and we binarize it and create a pattern. And we've generated a bunch of patterns, and we divide them into classes, and then we generate multiple variants of each of those patterns. And we basically create a large data set. It's a completely random data set of patterns. And then we train the cellular automata to basically learn those patterns. And it never sees the target data sets, which in this case are the MNIST and FMNIST data set. We also have an initial sparsity, which is about 20 to 40% on our cellular automata grid matrix. So how we train this is we actually have a combination of genetic algorithms and reinforcement learning to actually train the cellular automata system. So here's a small description of the hyperparameters that I used for the genetic algorithm. I use speciation to basically keep it from losing a strong set of species that were discovered. And there's a 20% crossover threshold, and the mutation is about 30% per generation. And those are the resultant hyperparameters that I was able to achieve for the cellular automata system. These are just the initial ones. We'll talk about how these were improved and modified moving forward. So to talk about the training paradigm, this is how I did it. So it's 100 generations of genetic algorithms, followed by reinforcement learning for 1,000 epochs or episodes. We do this combination because the genetic algorithms are really good at finding a wide search space and also from escaping from local minima. And the reinforcement learning is exceptionally good at fine-tuning and finding the really, really specific and really optimized parameters for the kernels. So by repeating this process again and again, we can actually, fine-tune and then escape from local minima if we're stuck in it, and then again fine-tune, and then thereby finalize a set of parameters that are very universal and generalizable. To calculate the error, we actually compare we actually have a Euclidean distance between the current sample and the centroid of the samples of another class, so as to maximize one class maximize the difference of separation from one class and all the other classes. That's how we train this algorithm, so as to basically produce the maximum separation between classes in that random data set. We then use that to calculate our fitness function, which basically averages this across the total number of classes present. And then we scale that by the activity of the cellular automata. As you can see, we have the reward function over here, which is the fitness function, which is the error, multiplied by the total number of active cells divided by the total number of cells present on the matrix itself. That tells you basically you're scaling it by the amount of activity present on the board. So if there's very little activity, you actually have a really low reward function because you want to encourage more activity across the board. And then the last, we use very simple Q-learning, where the states are represented by states are representative of the different kernel parameters that we were trying to optimize, and the actions are basically moving the parameters up and down in value of certain increments. So this is what the cellular automata evolution actually looks like. So you can take, for example, in the bottom left corner over here, you have a pattern X. This is an example from the data set. This is an example of the class X. And you would have multiple variations of that pattern within the same class, as you can see, variations with different level of variation. And you can think of this as different samples of the same class from MNIST or FMNIST. And what the cellular automata does is basically it reduces that variation down periodically over a number of time steps, and you can see it coalesces down to the same solution. Now, that solution need not be representative of the original class. It just has to be unique enough to be different from all the representation of the other classes. So it need not represent the input. It just has to be different from the inputs of all the other classes. And it basically reduces this space down. That's what the goal was. That's what it's trained to do. Now, when we actually apply this, we've trained it on this random data set, and now we apply this for testing on MNIST and FMNIST. We see that it actually does quite okay. And we tested it for 2 different sets of samples. So as you know, MNIST consists of 60,000 images. So we trained it for the entire 60,000 images, and those are the results in blue. And you can see that when you compare it against similar sized networks, so VGG11, VGG5, you can see that they do much better than the cellular automata system. But if we reduce the number of training samples down to 1,000, which is just 1%, less than 1% of the, approximately 1% of the data set, then the cellular automata seems to do and learn much, much faster. And it does remarkably well. So this is actually really good for low short learning when you have fewer samples to learn from. However, we noticed that, hey, it's doing okay, but there's something wrong. Like we're not able to, even though it's exposed to the network, it has fully connected layers after the, don't forget, there are fully connected layers after the cellular automata to still classify. So we were wondering whether we could improve this performance, and I couldn't figure out what was something was going wrong. So we also did a test where we checked how many convolutional layers are required to actually, like how many convolutional layers are required after 5 minutes left. Oh, okay. So how many convolutional layers are required after my cellular automata? So we noticed that we require a minimum of at least 2 cellular automata, or two convolutional layers after my cellular automata, 2 or more rather, to actually get a reasonable amount of performance. That tells us that convolutional layers are still required because the output of the cellular automata is still 2-dimensional, and convolutional layers are very good at exploiting that 2-dimensional data. What the cellular automata does is just reduces the load on the convolutional layers and thereby makes it easier to separate those patterns. So what I realized was what was missing was, because the CA doesn't actually see the data set, it kind of struggles with understanding how this new data set corresponds with the old data set that it was trained on. So what was missing was entropy. Entropy tells us what it's basically the amount of information, which can be defined in a lot of different ways. So as you can see here, empty system would be a 0 and a full system would be 100% entropy. The difference would be 100%. So we could incorporate this entropy into the network and thereby give it additional information to make a decision on how to treat the inputs. So you can see here there are different variants of this entropy, which is sample to sample correlation. There's correlation between samples within a class. Then there's total relative entropy, which is the total entropy of a system compared to the size of the grid. So it tells us how active that input is, how much space. So MNIST digits, if you've seen, occupies about 20 to 50% of the total space in an MNIST grid. There's also fragmentation that tells us how fragmented and distributed these patterns are. And also there's inter-class variance, which measures the variance between samples within a single class, telling us how much noise there is in a parameter space. So these, when they are factored into the learning process, then the AI can make a better decision, and the cellular automata can actually show significant improvement in performance, going and being able to do really, really well, and almost, well, not match state of the art for full performance, but does really well comparatively for especially in low short learning scenarios. And the last part is how we extended this to temporal sequences. So basically, we made the temporal data set where we made the same MNIST and FMNIST into sequences. And we're passing those sequences into activity recognition data module, where we basically blend each subsequent frame of the input into the cellular automata as it is running. And we use the same blending kernels that we had learned previously. And we perform this again and again, and then it can perform activity recognition over an entire pattern or a sequence. And what we notice is it does really well, and the entropy boosts its performance significantly, even in this state. And here we can see the actual trajectory over growing number of samples, of training samples. And you can see the stark difference between one sample and the full data set, and how well it does over tasks like comparative algorithms like convolutional LSTMs and RCNN for really low circumstances. I'm almost done. And the last test that we did was actually varying the number of classes as well as the sequence length to see how they affected the number of time steps required to actually reach a convergent solution. And we noticed that the sequence length actually affects it because, well, it's actually trying to memorize the entire sequence. So longer sequences affects the cellular automata, whereas number of classes is not that affected because that load falls upon the classifier after the cellular automata is done. And the last thing is the limitations are they're only limited to binary inputs and single channel data, and it's very poor for GPU parallelization. The future work actually focuses on my actual research, which is extending this for activity recognition in lifelong learning systems and trying to tell what task is going on at any point of time without a supervisor providing that context. So I'm hoping to also extend this to colored images so as to support that. As of right now, it's kind of limited to binary inputs and single channel data. So I'm working on ways to expand it. So thank you. Sorry, I went a little late.
Thank you, Tej. We have time for a couple of questions. Tom has a question. All right.
Thank you very much. Very good talk. So what's the performance ramifications of using cellular automata to replace a convolutional layer?
Right. So actually, cellular automata are more intensive, much more intensive than convolutional layers currently on GPUs. So when we did the static image analysis, it takes several more time steps for cellular automata because firstly, even if you have a large GPU array, cellular automata by their very definition are sequential. So it requires the previous state, so you can't parallelize them largely for the same input. So they take much longer. But when you translate that to temporal images, then as the input is streaming in, you can keep the cellular automata running. You don't have to wait for the entire thing. So for real-time data, it's really performant. And also because a large part of the GPU problem is transferring data in and out, cellular automata, since they are pre-trained and they don't need different filter weights to be completely put in and out, the same weights that repeat again and again and again, same filter again and again. So it's very optimized on GPU memory as compared to memory, basically. It requires less memory. But yeah.
All right, we have a question from online. Osama Youssef is asking, is there a possibility that the network is learning to classify MNIST or fashion MNIST just due to the convolutional layers and the fully connected layers, and that the cellular automata is acting just as a source of noise?
That's a good question. So you're saying that the two convolutional layers after my cellular automata would be taking the weight of the entire neural network. So you're saying if I could eliminate just have my two convolutional layers, yeah, maybe, but did I test that? I actually don't know. I do need to test that, I think, then to see if the convolutional layers are really, the cellular automata is really pulling its weight in that area. But when I test it against other systems with more convolutional neural networks, with more convolutional layers, we noticed that actually removing those layers greatly affected the performance. So, but I didn't test with the vanilla network, just with the two systems. I do need to do that test. Thank you.
Well, thanks a lot for your talk. I was wondering if we could go to slide number 14. You might have said that and maybe I missed it.
14. Yep.
So why is it that the accuracy of your network is going down with the network size?
Right. So here's the thing. So the larger the network size, the more time it takes to the GA and the RL to optimize the hyperparameters, and we gave it kind of limited time. And as the dimension of the CA grid increases, the number of parameters that need to be optimized increase exponentially. So actually it takes much longer for the larger grids to converge to a stable solution. So there's larger variation given the larger grids.
And would you conclude that this is only good for like smaller networks and smaller data sets?
Definitely for smaller images. So even if you have a larger image, you would have to reduce that dimensions to a smaller image. So the MNIST was 28 by 28. We reduced that to 10 by 10 and obtained the best performance for a cellular automata of 10 by 10, even though the input size was 28 cross 28.
Okay, thanks a lot.
I think we can probably move on to lunch. Katie's going to give us some instructions. Thank you very much, Tej.
Of course. Thank you.
Okay, so due to COVID restrictions, hopefully room 2 can hear me. Room 2, you are clear to go to lunch now. You will take your lunch back to room 2. But you all will go out right in front of room 1. There is a buffet set up for lunch. For everybody here, feel free to mingle while we're waiting for our turn, and I will let you know when you are good to go for lunch. Also, feel free to switch rooms if you would like. We're just keeping it around